Hello everyone, welcome back to today's video session on determination of reservoir storage capacity under irrigation and water resources engineering. Reservoirs play a major role in storing water for irrigation, drinking water supply, hydropower generation and flood control. However, determining the correct storage capacity is a critical engineering task because it directly affects project efficiency, water availability and reservoir life. In this session, we will understand different storage zones, sedimentation impacts, mass curve analysis, trap efficiency and monitoring methods used in reservoir studies. We will also learn how engineers estimate useful reservoir life and manage sedimentation problems. By the end of this video, we will gain a clear understanding of how storage capacity is determined and maintained in irrigation reservoirs. Let us begin with the basic storage zones of a reservoir. Reservoir storage is divided into different categories based on function and operating levels. First is dead storage, which is the portion below the lowest outlet level. This zone mainly stores sediment deposits and is not normally used for water supply. The second zone is live storage, which is the active storage used for irrigation, hydropower generation and water supply. This is the most important part of the reservoir for daily operation. The third category is flood storage, which temporarily stores excess flood water during heavy rainfall and reduces downstream flooding. Determining these storage zones correctly is essential for ensuring reliable water supply to downstream users. Engineers must carefully balance irrigation needs, power generation and flood protection while designing a reservoir capacity. One of the biggest challenges faced by reservoirs is sedimentation. Sedimentation enters the reservoir mainly due to soil erosion in the catchment area. When flowing water enters the reservoir, its velocity decreases, causing suspended particles to settle at the bottom. Over time, this reduces the effective storage capacity of the reservoir. Live storage depletion directly affects irrigation reliability and water availability during dry seasons. Continuous silting also reduces the overall lifespan of the project. Another serious issue is the impact on spillways and outlet hydraulics, which may become less efficient due to sediment accumulation. Therefore, sedimentation management is an important part of reservoir planning and operation. Without proper control measures, even a well-designed reservoir can lose its usefulness much earlier than its expected lifespan. Next stage is ideate. To determine reservoir storage capacity, engineers commonly use a graphical method called the ripple diagram or mass curve analysis. In this method, cumulative runoff is plotted against time. The slope of the curve represents the rate of inflow into the reservoir. By analyzing the curve, engineers can estimate the required storage capacity needed to maintain a constant water supply or target yield. The method also helps to identify critical dry periods when stored water becomes essential. An analytical alternative approach is sequence peak method, which calculates storage requirements mathematically. Another important method used in reservoir capacity determination is the area elevation curve method. In this approach, contour maps of the reservoir are studied. The surface area corresponding to different elevations is measured using planimetric techniques. Then reservoir volume is calculated using numerical integration methods such as trapezoidal rule. These calculations help define important operating levels like full reservoir level or minimum drawdown level. This method is useful for tracking sediment distribution patterns over time. Next stage of design thinking is prototype. Now let us discuss trap efficiency, which is a very important concept in reservoir sedimentation studies. Trap efficiency is defined as the ratio of retained sediment to total incoming sediment load. In simple terms, it tells how much sediment remains trapped inside the reservoir. One commonly used method for estimating trap efficiency is Brune's curve, which relates trap efficiency to capacity inflow of the reservoir. Larger reservoirs with higher storage capacity generally trap nearly 100% of incoming sediment. However, as the sediment accumulates and storage capacity reduces, Trap efficiency gradually decreases. Next method is testing stage. Reservoir monitoring is necessary to evaluate sedimentation and validate design assumptions. One common method is conducting post-monsoon hydrographic surveys to measure storage changes after every rainy season. Modern technologies such as echo sounders and differential GPS systems are used for accurate depth and location measurements. Reservoir life is generally defined as the time required to lose about 50 to 70% of life storage during sedimentation process. Engineers use monitoring data to compare actual silting rates with predicted values. If excessive sedimentation is observed, mitigation measures such as catchment area treatment, afforestation, and dredging can be implemented. Continuous monitoring ensures sustainable reservoir operations and helps extend project life. Let us summarize the important aspects discussed today. Reservoir storage capacity is determined using storage analysis and methods such as mass curve analysis and area elevation curves. Sedimentation reduces storage capacity over time and affects project efficiency. Trap efficiency and Brune's curve help engineers estimate sediment retention and useful reservoir life. Regular hydrographic surveys and monitoring systems are essential for evaluating storage loss and planning mitigation measures. Sustainable reservoir management requires balancing storage needs, sediment control, and long-term operational reliability. Understanding these concepts is extremely important for irrigation engineers because reservoirs are critical components of water resource systems. This slide presents the key connections involved in reservoir performance. The first branch is inflow estimation using mass curve analysis. Second is capacity loss estimation through sedimentation and Brune's curve. The third branch focuses on operational levels such as full reservoir level and MDDL. Finally, the fourth branch deals with reservoir lifecycle management through testing and hydrographic surveys. This conceptual mind map framework helps engineers understand how different factors are interconnected in reservoir planning and operation. Modern AI and analytical tools can further improve prediction accuracy and decision-making efficiency. Now let us test our understanding with few interactive questions. Here is the riddle. I decrease as silt increases, but without me, downstream crops will not grow. Who am I? The answer is storage capacity. Next, if trap efficiency is 90% and inflow sediment is 1000 tons, how much sediment is retained inside the reservoir? The answer is 900 tons. Another brainstorming activity is to suggest one nature-based solution for sediment control. Possible answers includes afforestation, watershed management, contour bunding, and check dams. Such activities help improve conceptual understanding and practical thinking skills. These are the important references used for this presentation. To conclude, determination of storage capacity is a vital process in irrigation engineering because it ensures reliable water supply, flood control, and sustainable river operation. Proper sedimentation analysis and monitoring are essential for extending reservoir life and improving project efficiency. Thank you for watching this session. I hope this video helped you understand the concepts of reservoir storage capacity and sedimentation management clearly. See you in next class. Have a good day.